Hi, so today we're going to be talking about the chain rule, which is one of the most important rules in calculus, especially in real one-variable calculus, but also it can be extended to multivariable calculus and complex analysis. Well, the thing is that this theorem tells us how to differentiate a function that is a composition of other functions. And it's going to be fundamental in physics, mathematics, engineering, even in chemistry and many other branches of science. And any time that you actually have to take a derivative, it's most likely that you will have to deal with the chain rule. And today we're going to be discussing a little bit about what the chain rule is, what it says, some conditions, right? The necessary conditions for it to be applicable, a brief comments on the notation that I'm going to be using because it might be a bit confusing, and of course the main dish of our video, the proof that we will be doing right here. So first of all, let me just say that I got this proof from a wonderful book called Calculus by Purcell. I'm going to write his name here. Okay, so this is a wonderful book, and the proof was on an appendix at the end. And there are many additions to this book, but it's anyone that you get, it might be wonderful. Maybe the later editions will have the property that they will have another chapter dedicated to ordinary differential equations, but in most cases, most editions, it goes from the basics about some basic mathematics that you need. Later on, it goes into limits. It explains what a limit is in an informal matter, so you can understand in an intuitive matter, and then it goes right into the formal definition. Afterwards, it goes to derivatives, differentiability, integrals, multivariable calculus, even vector calculus. And as I said, well, in some later editions you might even find some comments on ordinary differential equations. So, well, what matters to us today is that we're going to be dealing with the chain rule. So, let me just say that, well, let's just state the problem, okay? So, let's just state it. Let's say that we have a function, let's say sine of another function, 3x. Okay, so we have one function which is sine of x, but this is composed by another function which is 3 of x. Okay, so to take the derivative with respect to x of this function, what we have to do is take the derivative with respect to the inside function. Okay, this will be written like this: derivative with respect to 3x of sine of 3x, and then multiply by the derivative of the inside function, which is the derivative of 3 of x dx. Now it might seem a bit confusing, okay, this is a 3, because maybe this notation you haven't seen so often, and in fact it's not really a good notation, it's too long and, well, it's not really used. But it's the notation that I prefer to use when explaining things, because it shows clearly what we're doing. We're taking the derivative of this with respect to this, which is the same as writing, if we define u equals 3x, we can rewrite this as the derivative with respect to u, which is 3x, of our sine of u, which is 3x. Then this is just our cosine of u, which is just cosine of 3x. And afterwards, okay, so let me just write that here. Okay. Okay, so we have that this, as we saw earlier, is just the cosine of 3x. And now we have to multiply by the derivative of the inside function, 3x. And this is just a regular derivative, and it's just 3, okay? This is a simple case, but it can apply to any functions that you have. Okay, so let's just, that was just a quick example to see what we're dealing with, but let's just get on with what the theorem says. It says that if g of x is a differentiable at x equals a, okay, g of x is a real function, g of x takes me from an interval, let's just say x1, x2, which is contained in the reals, to a real number. Okay, so this is a real function of real variable. So if it is differentiable at x equals a, and if another function, let's just say f of g of x, it also goes from a set, but instead this set is going to be g of x1 g of x2 this is another real function, it's just another name. You can even call it h of x because it is in fact a function of x. Okay, but let's just forget for this about a minute and just get on with this. If g of x is differentiable at x equals a, and f of x is differentiable at g of x equals g of a, then f of x is differentiable at x equals a, and this is the expression for the derivative. What does this really mean? This means that if we take the derivative with respect to x of a composite function, f of g of x, at a point x equals a, we have to multiply by the derivative with respect to the inside function as we saw earlier, evaluated at g of x equals g of a, times the derivative with respect to x evaluated at x equals a. Now, it might seem a bit confusing, but with time and with many examples, you might get used to it. Or you should get used to it. But well, what does it mean that g of x is differentiable at x equals a? This just means that the derivative with respect to x evaluated, this means evaluated at x equals a, right? So we take the derivative and evaluated at x equals a, is equal to, well, the definition. The limit when a little increment in x goes to 0 of our function, evaluated at that point, but a little farther away from the point, an increment in x, minus the function at that point, over the increment in x. If you're not really familiar with this definition, or where this comes from, I will put links in the description where I will be discussing this in more detail. But here I'm just gonna do a quick recap. So if it is differentiable, we are saying that this limit exists. Likewise, if f of g of x is differentiable, g of x, careful, this is g of x, okay? This is the weird derivative of g of x, and we evaluated at the point g of x equals g of a, then, well, this limit must exist. And what is this limit? It's just the same as before. But instead of taking an increment in x, we take an increment in x, we are taking it in g of x. So here we have just g of x. F plus my increment in g of x, okay, minus f at g of a over the increment in g of x. So we are assuming that this exists and that this exists. And then the consequence of this theorem, which we will prove now, is just saying that f of g of x is also differentiable at the point x equals a. That is, that if we take it this time with respect to x, careful, not g of x but x, and evaluate it at x equals a, we get, well, the same as before. We increment in x this time, just like here, f of g of a plus the increment in x, over increment in x, this exists, okay? So this is what the theorem is telling us. Well, there's another kind of notation that it's more compact, and it's Leibniz notation. This is like a variant of Leibniz notation, but I just put the function right here so you can understand it better. But Leibniz notation says that if I have a function c equals, for example, f of g of x, and another function g of x, then the derivative of c with respect to x, which could be this evaluated at x equals a, is equal to the derivative of c with respect to, let's just call this u, with respect to u, evaluated at u equals, let's just say u naught, it being g of a equals u naught, times the derivative of g of x, of u with respect to x, and of course again evaluated at x equals a. Right, so this is a more compact notation than this one, right? But all we're doing is just rewriting f of g of x as z and u as g of x, right? Yeah. Let me just check. Yeah, that's it. Now another kind of notation, which is even more compact, is Lagrange's notation. Well, it just says that if we defined, yeah, like this, c equals f of g of x, c is a function of x, then we can write this as the derivative with respect to x of this is equal to the derivative of this with respect to u, and we can just denote it as f of g of x. And let me just write here an a, right, to denote that we're evaluating it at x equals a. So this means take the derivative of this with respect to x, and this means take the derivative of this with respect to the inside function, which is g of x, which would be this. Now, times g prime of a. And this is just a regular derivative with respect to x evaluated at a. So I hope that the notation is clear. This might have been a bit of a long introduction, but I just wanted everything to be clear. Also, as always, I will have a PDF in the description where I will have all of this done nicely in LaTeX, and also I will have my references, maybe some interpretations, some history, and well, many. Okay, so now that we've made some comments on the notation and what we're dealing with, let's just get on with the proof, okay? So, what's the first thing that we are going to be doing? Well, we're going to be defining a function, and we're going to give it this name. We're going to just call it epsilon of the increment in g. And how are we going to define this function? Well, we're going to define it as the approximation of the derivative. Okay, so let's just say that we have the derivative of f of g of x evaluated at g of a. Using Lagrange's notation, we would be on this case. Okay, we'll be using this notation for the proof because it's easier and it's really shorthand notation and it's more useful. Okay, so this just means this derivative. And what is the approximation? Well, the approximation is just this, but without taking the limit when the increment in g goes to 0. So we will just have this, plus my increment in g minus f of g of a. Okay, so this is an approximation. This is not exact because we are not yet taking the limit. But of course, just like any other approximation, there's something that's off, right? There's the error. And the error in this case is going to be called like this. And well, we can just say that this is equal if we add our error, right? So this is just the definition, the error. Nevertheless, for the theorem, we're going to define it in a different way. We'll just say that this is minus, okay? Why minus? Because this is not really a relevant fact, but we're going to be defining this the other way around, right? If we isolate here the error, we would get this minus this. But to prove this theorem, we're going to be defining it the other way around. For example, well, let's just do it. We're going to be defining this as f of g of a plus my increment in g minus f of g of a over my increment in g minus f prime of g of a. Okay, so notice that if we, as I said, if we isolate this, we will get this minus this. But instead, we're defining it the other way around. We're defining this minus this. Okay, this is just for the proof. Okay, this is just relevant for the proof. But the error would actually be written like that. So that's why we are gonna put a minus sign here, so you don't mistake it with the actual error. So, okay. Now what's the thing that we're gonna do? Well, first you just have to notice that this is not 0. Okay, the increment in g is close to 0 if we take the limit, but it's not 0. And now we're not even taking the limit. So we are gonna be defining the increment just like we always do. The increment in g is my g evaluated at the point, but with a little increment, delta x minus the function evaluated at that point. Okay, so that's just what it is. We can expand this, but we're gonna be doing it later. For now, you just have to notice that this is not 0, so it's okay that it's divided. Now, if we multiply everything by this increment in g, what we get is the increment in g times this error, this minus error, if you want to call it like that, f of g of a plus my increment in g minus f of g of a. minus my increment in g, because we're multiplying everything by increment in g, times f prime g of a. Now, the next thing that we're going to be doing is just dividing everything by the increment in x. And just like before, the increment in x is not 0. It can approach 0, and in fact it will do it later on, but it is not 0. So, for practical purposes and theoretical ones too, we can divide by it. So, let's just divide everything by this. And just to write less, I am going to do it here. We divide this by the increment in x, we divide this by my increment in x, and we divide this by my increment in x. Okay. I'm running out of chalk, so I just want to switch. Let me just write this a bit nicer. Okay, so this is what we have so far. And it can remind you of the derivatives we have here, because in fact it will become the derivatives, but not yet. We have to do a little 2 or 3 things before. So this can be rewritten in this expression, and also we can rewrite this and that. So here we just plug this in here, and we have that g of a plus my increment in x minus g of a over my increment in x times my error, right, my negative error, if you want to call it like that, is equal to this expression. But wait a minute, because what is g of a plus this? Well, this g of a cancels with this one, and we just get this. So in fact, this is f of g of a plus my increment in x, right? You just do that if you don't see it, but this cancels with this, and we get this. Minus f of g of a over my increment in x. Minus, I'm just going to write it here, f of g of a plus my increment in g minus f of g of a times my derivative again. Now, the next step is taking the limit when the increment in x goes to 0, because in that case we will get that this is exactly this expression, and we can substitute it by this. And we just have the derivative of g of x evaluated at a. Likewise with this, we will get this expression right here, and with this we will get this expression. No, sorry, this expression again. I'm getting mixed up myself. No, yeah. Sorry, this is wrong. This is the derivative of g of x, sorry. Made a mistake there. Now it's correct. But the thing is, what is this when x goes to 0? Well, let's just do it. Let's just see what it becomes. I'm just going to erase all of this. So from the definition we saw earlier, we saw that, well, this increment in x, in g, sorry, is just my approximation, right? F of g of a plus my increment in g minus f of g of a minus f prime. Now, how have we defined f prime? Well, we have defined f prime here as the limit when the increment in g goes to 0 of that. So if we isolate this, I'm just going to write this here, because this is like an incision, right? It's just a separate thing just to calculate this. So f prime of g of a from this expression is equal to my approximation. I'm just going to write it here, my approximation, right? Minus my error, my negative error in this case. Now, if we take the limit when the increment in g goes to 0 in all the equation, this tells the same because there's no increment in g here. So the limit when increment in g goes to 0 of this is just this. The increment, the limit when this the increment goes to 0 of this is just, well, the limit when g goes to 0 of this. And, well, we have to do this limit too. Now, for this to be equal to this, as we have stated before, which is one of the conditions of the theorem, that f of g of x is differentiable at that point, because we know that this has to be equal to this must go to 0. So we get that the increment in g goes to 0, this implies that my negative error of g is also going to go to 0. Right? Because we need that this just goes to 0 and cancels out, so we have the equality. Okay, but here we want to take the limit when the increment in x goes to 0, not when the increment in g goes to 0. So let's just see what happens when the increment in x goes to 0. Well, what is the increment in g? It's just this, right? It's just g evaluated at a, and g minus g of a. Now if we take the limit on both sides, we get that, well, this goes to 0 is just, this just stays the same, because there's no actual increment in g there, increment in x, sorry. And when we do this, well, this should go to 0, and we get g of a minus g of a, which is just 0. So we get that as the increment in x goes to 0, this implies that the increment in g goes to 0. So increment in x goes to 0, well, then it follows that this goes to 0, and if this goes to 0, then it follows that this goes to 0. So if we just take the limit when the increment in x goes to 0 of all of these, we get that g of a plus my increment in x minus g of a over my increment in x well, if we take the limit, this goes to 0, this is finite, so all of this just goes to 0, okay? And also, well, we can just rewrite this as taking the limits of this expression right here, f of g of a plus the increment in x minus f of g of a over my increment in x. Minus, yeah, what we have right here. And what is the limit when we, well, let's just write it and figure it out afterwards, but we already know what this is going to give us. Okay. Okay, so this is what we get. We can just erase this and just put a 0 in there. And this is the expression that we get from just following some steps by defining this function. Now, what is this? This, if we go back to our definitions or our expressions for differentiability, is just the derivative with respect to x of this, right? Because we have that expression here, so that is just this expression. So let me just write it down here. That is, this is just this expression. So we have that derivative with respect to x of f of g of x evaluated at x equals a is equal to, well, if we take this to the other side, it is equal to this limit, but this limit is just, as we saw here, the derivative with respect to x of g of x. Of course, evaluated at the point of the point in question, times f prime of g of a. So let's just write this here. Let's just write this one first. Times the derivative with respect to x of g of x at x equals a. And lo and behold, this is our expression, this is our chain rule. The derivative with respect to x is equal to the derivative with respect to g of x times the derivative of the inside function. And well, we have found the theorem, so we can just make a little square that we prove the theorem. And this should be our result. Now, this result is I cannot stress enough how important it is, above all when we're dealing with multivariable functions or functions with many functions inside. But of course, this is not yet applicable to multivariable functions, but it's easy to generalize it. I will make a video on this kind of generalization. Well, that's all for today. I hope you liked the video. Be sure to check the description for the PDF and more interpretations and comments, and of course the references, and well, see you in the next video.